Good morning, good day, good afternoon. I'm very pleased to give you a lecture regarding refraction at a spherical surface. So essentially what I will be doing in this lecture is that I will use this as a starting point to understand how thin lenses behave. So this is the kind of first lecture on our way to understand thin lenses that we will be speaking about in the next lecture. And from the kind of engineering point of view, I would like to point out that spherical surfaces, they are by far the most common types of non-planar surfaces that we can make and use. So they are very easily manufactured basically by polishing a piece of a glass. So spherical surfaces can be very easily made in mass quantities. And of course, although such a surface and spherical lenses, basically lenses consisting of spherical surfaces, although they are not ideal in terms of their behavior, especially in terms of their aberrations. In practice, they work quite okay. And I would say that most of the lenses that we use and buy in optics, they are spherical lenses. So that even though they are other lens types, aspherics, freeform lenses, and such, most of the time we are dealing with spherical surfaces. So aberrations in practice, when we are smart putting many spherical lenses together, we can actually even minimize aberrations to a good degree, so that even though we know that they are not ideal in practice, most of the time spherical lenses are not as bad as one could think of. So please do not wrongly judge spherical lenses and spherical surfaces. And with the mathematics, we will start with the introduction of Snell's law. So essentially how a light is being refracting at an interface between air and a glass material. And we will introduce the partial approximation shortly afterwards. And that will be our means to really simplify dramatically the associated math. So essentially we will linearize the problem so we get rid of the sines and cosines. And that really dramatically simplifies our treatment. And then this is absolutely what is needed in geometrical optics, so that we really need this approach to simplify the math. But maybe I should warn you already that if you want to go beyond and you want to understand aberrations, then it will be the partial approximation, this assumption that you should then critically look into, and you should not anymore just make the simple Taylor's approximation of the sines and cosines, but rather you should take also the next follow-up terms in your Taylor's expansion. But more on that, of course, in the follow-up lectures, and maybe as a homework exercise. Let's see. And then finally, I will be introducing to you how we can define focal planes and focal points of the spherical surfaces. And this will be a nice ending thing to do, because then we can understand how thin lenses will be behaving. So essentially, once we get into the thin lens equation, once we know where the object point resides, and once we know what is the focal length of our lens, we have essentially solved the imaging problem, and we know where the object is being formed and how it looks like in terms of the location with respect to the optical axis and so forth. So this is what I will be speaking about in this lecture, and I will now get started with the actual message. So most of the optical instruments, as I already mentioned, they consist of several lenses, and from the manufacturing point of view, most of these are actually spherical lenses. And why this is the case is that the spherical lenses are by far the easiest to manufacture. And this is the case because they can be polished, so we can take a piece of a glass, and then we can polish that piece of a glass to form a lens where we have spherical surfaces on either one side of the lens to make it a plano-convex or concave lens, or we can have spherical surfaces at both sides of the lens. And depending on how do you polish, you can actually make quite different types of spherical lenses subsequently. A single spherical lens, and you could of course also make a system that consists of many such lenses. This is not the ideal one. And what I mean with the not being ideal is that we will have spherical aberration, and we will have also other aberrations present at spherical lenses when we are using spherical lenses. So this is not always the best scenario, and if you would have money, of course you can do better. You could design more arbitrary looking lenses, but many times it's actually easier to instead of taking a single lens component, you actually take several lenses and you adjust their changing parameters, essentially the radius of curvature, the materials, there's like a relative separation, and then you could actually make a instrumentation that behaves quite okay in terms of the actual amount of aberrations that are present. And then finally in your application of interest, it's really often a compromise that how complicated of a system you want, what is the price that you can pay, what is the kind of maximum cost you can have from the optical instrumentation, and what you want to do in terms of these parameters that you can change in your kind of problem statement. For example, like as an example of this kind of like a challenging design problem would be the cameras in our mobile phones. Everybody has a mobile phone nowadays, maybe even several, and everybody has at least one camera in the mobile phones nowadays. There seems to be an awful many. I think I have 5 or something in my own mobile phone on the backside. And there, the kind of space limitation for the lens system that we can use to actually make a imaging instrument, so basically making a camera, it's quite limited. And then also there's a lot of cameras, and then the price of a mobile phone is not that much. So there's also these criteria that are associated with the designing problem, that how we can also make it quite cheap. And then the camera companies that are making cameras for the mobile phones, they don't even tell what's actually happening nowadays with all that stuff, of course. And we do not even know how the detector array, so essentially the kind of camera detector array, how that is being, what kind of image it's actually being recording, and how much magic is taking place computationally afterwards. So we do not even know what's actually happening, and I guess it would take quite a bit of reverse engineering to figure out like what is actually done nowadays in the real mobile phone cameras. So that's just a principal example of some kind of system that is quite relevant, and then the kind of markets and the amount of optical instrumentations that we are speaking of, like we are speaking of millions, hundreds of millions of cameras easily, billions of cameras easily, by just looking at how many mobile phones we have in the world right now. So sorry, I was heavily branching out into somewhere else. So I was speaking about spherical lenses, and there's about the fact that you can also have other kinds of lenses. Another type of a lens that is not spherical, we call these kind of lenses aspherical or aspherics. And of course, this is what the name means, terminology means here, that if it's not a spherical surface that is inside or forming the surface of the lens, then it's not a spherical lens, but rather aspherical. And these, of course, can be used. And they work nicely, especially for their like very specific applications. So if you are lucky, if you, for example, do not want to image, but rather you want to focus light into a small spot, and you have a nicely collimated beam that you want to focus light, then you could easily buy a spherical lens that you can quite nicely like use to focus light. The prices of them are only like some tens of euros for a single spherical lens, so it actually works quite nicely. But usually like it's quite limited in terms of specific application range that you can use the single lens for. So if you want to do imaging, aspheric lenses usually are not the best solutions, so that that's the kind of downside of them. They're quite cheap, but many times their kind of capabilities are quite limited and restricted to only very specific applications. There's also a possibility to make a freeform lenses. So essentially there you would not even be restricted to some kind of like a slightly non-spherical surfaces, but you could actually like design all sorts of almost arbitrary looking lens shapes. And these can be 3D printed even nowadays. So for example, in the University of Eastern Finland, I think there's even research, and I think startup companies that are using these kind of freeform lenses and making actually products out of them, so that these kind of possibilities exist there already. And I would imagine that these kind of possibilities will be becoming more and more important when time is going forward, so that this might be actually quite interesting for you to have a look on if interested in kind of designing lenses and so forth, or at least check on the status what is the status currently, maybe ask ChatGPT or something that what's a freeform lens and what is the current status, and probably you get a good nice overview of the kind of status right now. Okay, so our focus in this lecture, and especially like in this course, will be to understand how a spherical lens behaves. And other lens types, although they do exist and they have their like related properties, we do not consider them here, but we will only like mention them and leave their treatment into the follow-up courses. But of course, if you really want to understand how they behave, like you know what a Snell's law is, you can really understand how the refraction takes place in that kind of lenses. If you want to understand them, of course, the physics doesn't really change. It would be just that the kind of surface here would not be a spherical one, but rather a non-spherical. And then what would happen here in each location, of course, this is entirely governed by the Snell's law. So from that point of view, new physics would be awaiting for you there, rather just a different kind of applications and more complicated mathematical treatment. So let's consider, as in the figure, the blue medium there, that would be an optically transparent medium, given with a refractive index of N2, as shown in that figure. And let's assume that we have one surface that is a spherical one, and that is associated with a radius of curvature of R. The center point being at C, as shown in here, at the end of the dotted line here. So this would be the center point. So the radius of curvature R gives me this distance. So here, the blue material here is basically optically transparent, so that the light is actually happily being propagating through. And here, this is a spherical surface that we consider here. So that we must consider what happens here via the Snell's law, and that's it. We consider an object point right now that is at the optical axis. So here is our point of an object, and we want to understand how this gets imaged through our single piece of interface into somewhere here. And here the axis, the optical axis, essentially is going through, and it's normally incident at the interface. So the object point S is at a distance of S0, so S or S object from the surface. This is a common piece of terminology, and the image point P is at a distance of SI, as in image. And both points, let's see them that they are being connected by a line, so that would be our optical axis, and the optical axis is coming at a normal incidence through the interface, as shown in the figure. So this is our problem, and this is how the geometry looks like, and now we want to understand where the image is being formed and how it looks like. So the ray of light that leaves from the point S, so that would be our object point, it leaves at an angle of alpha that it makes with respect to the optical axis. And this ray of light faces the surface, the interface, at a point A, as shown in the figure. And what happens there is that it refracts based on the Snell's law, and then it starts propagating towards the image point. And the Snell's law applies for the respective angles, of course, so that we have the refractive index profile of our outer medium, Ni, and that would be in the refractive index of air, as most of the time we are having lenses in air. Then we have the sine of alpha plus theta, because phi, so that we are drawing a surface normal here at the local interface location point. And then the angle of incidence, of course, as we can see, is that it's actually not just the alpha, but are also a alpha plus phi here. And then on the right-hand side of the Snell's law, we have the N2. That would be most of the time the refractive index of glass or whatever would be our lens medium. And then we have the refraction angle, and now it's phi minus beta, as can be seen in the figure. So here, please note, using the C point, the center of our curvature here, we can draw the image normal quite nicely, and then by just looking at that, we can easily see that how the rate of light is actually being propagating into the image point here. So N1 is the refractive index of the surrounding medium, and from the figure, what we can see is that if you would want to calculate the alpha, we could either do that by just calculating, not alpha, but we want to go into the kind of different parameters. We want to describe how we want to understand what would be the kind of distances SO, what with respect to the SI, and essentially like how strongly the light is being refracted here. But in order to solve the problem, we need to go through a little bit of math. So let's look first at the tangent of alpha. So looking at the figure, we can see that that's the height of my point A from the optical axis divided with the SO, the object location from the interface, and then we have this difference marked here with A. So that is the separation between the ear glass interface and the actual continuation of the point A towards the optical axis. So this is, as you can see, is basically the tangent of alpha, and we can use the same kind of trigonometry to calculate the tangent of beta angle, and that would be then the same h divided by si minus a. And then we can also calculate the sine of theta, so that's h divided by r. So as we can see here, we have the sine here. This is also the same sine here, and then we can see that we have the h and we have the r, so we can definitely write the sine of theta to be, phi to be h over r. And then finally, we have the a parameter, and that's essentially r, the radius of curvature, minus r times cosine of phi. So this is what we can just like take by looking at the figure, the geometry of our problem. And now the trouble is that this is actually a system of equations that is not linear. So in fact, it's transcendental. So if you would want to solve that with respect to the parameters of interest, we would not be able to solve that analytically. So what we must do is that we need to somehow use approximations to get forward. So essentially what we will do is that we will look into solutions where the ray of light propagates approximately along the optical axis. And in fact, it turns out to be the case that most of the time this is a pretty good approximation. And in this case, what this means physically is that all the angles are small. And this results in the case that we can approximate, for example, the sine of phi, the Taylor's expansion, that it's basically just phi. And then the same thing, cosine of phi, small angles, this is essentially just unity. So this we can manage by just taking the Taylor's expansion and getting rid of all the interesting terms in the Taylor's expansion. And I will spoil it already that if we would want to go forward and we would want to go understanding mathematically the aberrations, we would not be happy with these approximations anymore, but rather we would take the subsequent terms from the Taylor's expansion so that we would have something here. And those terms would be then considered mathematically how they affect the image formation, and consequently we would see what kind of aberrations would be arising because of these terms. So this is mathematically what would be done in order to understand lens aberrations. But we do not do this at all. We're just happy with our approximation here, and this is known as the paraxial approximation. And the kind of regime we're dealing with is also known as the paraxial optics or Gaussian optics, so that we have happily linearized the system of equations, and then we can nicely solve that. And no, most of the time this is actually a pretty good way forward, because it doesn't really affect the kind of image formation processes, that how good of an image is being formed. Always the image will be formed in the same location, but rather it will be blurred slightly when we are taking into account the other higher order terms in the Taylor's expansions of the sines and cosines. But the image will be at the same plane, basically. So now with this approximation, we can really simplify the Snell's law. And the nice thing of that is that we can get rid of the sines. So then we are resulting ourselves with a simple linearized problem with respect to the angles. So now we have ni times alpha plus phi, and then on the right hand side we have n2 times phi minus beta, so no sines anymore there. And now we can even solve the alpha angle. So tangent of alpha, by definition, that's the sine of alpha divided by cosine of alpha, and this is approximately h over s naught. So let's say that the alpha term is, sorry, not alpha term, but the a term is small, so that in the original case we have s naught is object here plus a, and now a is quite small, so that then we can approximate the tangent of alpha is just h over so. And then tangent of beta, Similarly, we can get rid of the a, so it's essentially almost h over si, and then sine of phi is essentially h over r, so that we had the, well, this is actually like accurate, like this is actually like a accurate equality here by just looking at the original figure, so that this is slightly wrong of having sine phi being approximately h over r. It's actually exactly that. And this is based on the fact that we have the alpha, sorry, not alpha term, but the a term that is basically 0. So this is what we assume further. And now we can combine these to give a relation that looks like this. So you have the refractive index of our surrounding medium, and then we have things inside the parentheses. So we have h over SO plus h over r, and then on the right hand side we have n2 times h minus r minus h over si. So this is what we have. So essentially just note like a tangent of alpha, sine of alpha is basically alpha, cosine alpha is basically unity. So we get this, and then we have alpha here. So tangent of alpha is basically almost alpha. So we can plug into here this guy, and then we have this phi term here, and then we can just plug from here. We essentially get that the sine phi is almost phi, and then this is essentially h over r, and then we can plug this guy into here, and same thing with the terms in here, so that we just basically use these, and we plug them into the approximated Snell's law to get this relation that we see here. And this we can further reduce into a form that where we have on the right hand side, we have the refractive indices n1 divided by SO plus n2 divided by SI. And then on the right hand side, we have the contrast between the refractive indices n2 minus n1 divided by the radius of curvature. And this we can see it doesn't really depend on the point of A's distance h from the axis, so that we can already see that in essence all the rays that we could draw like would be complying with this equation. And let's now look what this implies in terms of image formation, what this actually means. So let's apply this found solution to two special situations that have been highlighted in the figure in the below. In the A scenario, let's consider first that we have a ray of light that is propagating first along the optical axis. So basically, this is the optical axis, the black line here, and in the beginning, we have a ray of light that is propagating parallel to the optical axis into the interface. And now what happens is that essentially, mathematically, our object point, since it's propagating along the optical axis, the ray of light coming from the object point, object is essentially at infinitely far away. So SO is essentially infinity. And now what happens is that the image is being formed into a location which we call back focal plane. And this is a way how do we define what's the back focal plane location, back focal point. And at this case, it's essentially the Fi is the focal point, is essentially the image location Si. And now we can solve that this Fi is essentially in O2 over N2 minus 1 times R. So we are just using the previous slide's equation, and now we are plugging in S object point to be infinity. So that term dies out, and what we are left is that we have this. And now we are replacing Si with Fi, because graphically, like what we see is that we have a way to see that if a ray of light comes to our spherical surface, it will be focused into this point. And since this equation doesn't depend on the height where my interface point is, I can imagine that I have all the rays of light coming along the optical axis, propagating along the optical axis. They are hitting the interface, and all of these rays of light will be focused at the same point. So that thus it really makes sense that we call that as a focal plane or focal point. And especially because we are looking at the rays of light propagating parallel to the optical axis, we call it the back focal plane. And now the image point is denoted with a term capital Fi to kind of clarify that this is indeed the back focal plane. And what we will do next is that we will do the same thing, but now we will consider the other scenario. And now here we will want to know what is the so-called front focal plane or front focal point FO. And here the guiding principle is that we want to look into rays of light that after the interface, after refraction has taken place, these rays of light are propagating parallel to the optical axis. And when they are propagating parallel to the optical axis, basically that just means that our image location will be at the infinity. So let's now consider a ray originating from the point FO at the optical axis. Refraction takes place, like I mentioned, and now essentially the image will be formed at infinity. So SI will be infinity, since the rays of light, all the rays of light leaving out, they will be propagating along the optical axis. And now the object, we call that to be located at the front focal plane, and that we can calculate, and in essence, in this case, we can denote that the SO is equal to FO. And the FO, front focal plane parameter, can be calculated using the previous equation, and now it will be Ni divided by N2 minus Ni, N1 times the radius of curvature R. And please note here that the front focal point FO and the back focal point Fi, or yes, for a back focal plane Fi, they are not equal to each other. And this is that it takes place for a single interface. So we are not speaking about spherical lenses yet. But at least we're on our way there. We already see that a single spherical surface does refract light, and we can now understand how it behaves. And this is a very good starting point to understand how a kind of spherical lens behaves. And finally, let's list some of the sign conventions. These can actually be quite cumbersome, so please be careful when we are looking at the sign conventions with different kind of optical instrumentation, especially when we look at mirrors, you should be extra careful. This is a table that hopefully helps you that what happens. And this is important because when we are doing calculations, we must have the signs right so that we can actually understand what happens. So when the variable, the location of the object point with respect to the interface, when it has positive sign, it means that it's on the left-hand side of the surface. Similarly, if you have the front focal plane, when it's positive, it means that it's on the left-hand side. And if these variables are minus signed, then they are on the right-hand side. And of course, depending on what kind of image we have, when we may have either a real or virtual image. So if these guys will be positive, then we will have a possibility of having a real image. And similarly, we have these other parameters, and depending on how do we, what kind of sign they have, then their location will be different. And please note here that the convention is that if we would be having a image location that is on the right-hand side of our interface, then the sign is positive. So this is usually the kind of case. And then finally, the radius of curvature, that when we have a positive radius of curvature, that would be the scenario we just considered, so that the opening of my circle is towards the right. And when we have a negative curvature, then I have my opening towards the left-hand side. So essentially where the center of curvature is the point C with respect to the curvature. So this was all I had to say. And please join me shortly regarding the next lecture, where I'll be extending this to understand how a actual thin lens behaves. So in that respect, this was actually a prelude lecture to really understand the real thing, the good stuff, and how a actual lens being formed out of two spherical surfaces will be behaving. But more of that, of course, in the next lecture. Thanks for listening to me, and please enjoy the day. Thanks, and bye-bye.